So we're now going to look at a corollary to Fermat's theorem on stationary points. The corollary is as follows. Let's state it. Suppose f defined on some interval and c in AB is an extremal point for f, then one of the following three options has to hold. And here I have to say then at least. So I mean, more than one can be true at the same time, but not in any combination. So the first is that c is stationary for f. So that means f prime at c is 0. The second is that c is endpoint. So that means c is a or c is b. And the third is that c is singular for f. That means that f prime c does not exist. Here I can make a remark saying that the definition of what a singular point is for a function is different from book to book. This is something that's more natural to define in a more abstract setting, you could say. But given the assumptions up here, then I think every definition of what a singular point for f is would then be reduced to the same thing, namely that f prime does not exist. You could say that some books disagree whether or not the point has to be in the domain to be called singular. For instance, if you have f of x equals to 1 over x, it looks like this. 0 is not in the domain, but should you call x equal to 0 a singular point for f? In our course, we say no, we shouldn't. For a point to be called singular for a function, it has to be in its domain. If not, we don't care. But in other books, it's enough to be in a punctured neighborhood, you could say, of the domain of f, etc. And then you can put different requirements on the bad behavior you need to call a point singular. In any case, we call a point singular if it's in the domain and the derivative does not exist there, because we're only going to use singular points in the context of this result here. And in this context, that is the most natural formulation. So let's look at the proof. There's not much to do here. So this is basically just a proof by cases where each case is very short. So let's do first splitting into two main cases. So case 1, case 2. Let's do case 1, which is really simple. So up here, all we know from the start is that C is in AB. So let's now suppose that C is endpoint. So that's a possibility. I mean, C can be an endpoint. And then we're done, because now we arrived at one of the allowed conclusions. So it's kind of silly. But this leaves a slightly more interesting case. So now we can suppose C is not endpoint. Now we can rule that out and then focus on, okay, what happens then? Then let's split into another pair of cases. So let's now do case 2i. And what is that? Well, suppose f is differentiable at c. But then Fermat says, since we now have that, so c is not an endpoint, this means that c is in the open interval and we're differentiable there. This is exactly what Fermat needs to say that f prime c is equal to 0. And we're done. And now we do case 2i, and then suppose f is not differentiable at c. But what does this mean? Well, this means exactly that f prime does not exist at c. And again, we're done. So basically, what we've discovered here is that just by splitting into cases, if you have an extremal point or a local extremal point, so I should say here local, then well, either c is an endpoint, okay, so that's a possibility. Or if C is not an endpoint, well, we're at an inner point, and then, well, either you're differentiable there or not. If you are differentiable there, then you're a stationary point. If you're not, well, then you're a singular point. Done. So this theorem here, or this corollary here, is just bookkeeping, just keeping track of what the possibilities are. So we did not do much here, but it's really useful information to have.